Hey guys, I assume everyone here takes chemistry, right? Anyone take chemistry? Oh my god, you actually don't take chemistry. You got some food on your mouth, or maybe you want to wipe it off with some tissue or whatever. Please don't flick it on the floor because that's gonna get some rats in here. Go wash your face. Everyone, give me 1 minute, guys. This guy is like washing his face in the toilet. Okay, anyways, as I was saying, today we're going to move on to a new chapter. We're basically going to learn the structure of an atom. How to prove the structure of an atom is what we thought of. And then we're also going to learn what element symbols are. Basically, you know there are different elements, right? Hydrogen, helium, chlorine, magnesium, blah, 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 right? Usually this is the symbol for the representation of the element. Usually they'll have an element symbol here. It's nucleon number and proton number. We'll go more detail on that later on. Then we are also going to learn something known as isotopes. Isotopes are basically the same element as you can see here. All of them are hydrogen. With the same proton number, as you can see, all of them are 111 with different neutron numbers. You can look at the graphical representation now. These all are hydrogen. They have the same proton number, the red color proton as you can see here, but they just have different amounts of neutron numbers. Then they are known as isotopes. And finally, we're going to learn the difference once again between fusion and fission. But I just want to give a quick reminder that we actually went through this a little bit during the energy chapter, if you guys recall. Okay, but if you don't recall, never mind. Nuclear fusion, in a very summarized version, is the combination of two smaller nuclei to form one larger nucleus, right? Whereas fission is the exact opposite. Just now, this one is combined, right? This one is breaking apart. One neutron will bombard the nucleus and split them into two smaller nuclei, which has free neutrons to bombard other nuclei. Okay, so it becomes smaller and smaller and smaller. The main difference is that one combines and one splits. The common things that they have in common is that they both provide large amounts of energy. For example, nuclear fusion occurs in the sun, right? That's why the sun can continuously burn without any input energy from it, right? And nuclear fission occurs in the nuclear power plants, right? That's why nuclear power plants generate electricity for Japan. Okay. And after that, we're going to be doing exercises. Okay, so for the benefit of those that do not take chemistry, first and foremost, you are introduced to something known as an atom. Okay, an atom is mainly made of two main parts only. Number one, the center, known as the nucleus, where the protons and neutrons reside. Okay, so basically the nucleus contains the protons and the neutrons, right? And the outer part, which is known as the electron orbit, right, where the electrons float around. Different atoms or different elements will have different amount of protons, neutrons, and electrons. And it's because of the composition of the electron, the proton, and the neutron, which makes up different elements. Okay, for example, maybe hydrogen only has one proton. Okay, after that, magnesium have two, and so on and so on, and all the elements. You can refer to the periodic table, right, if you want to. But I'm sure you wouldn't. One thing I do want to highlight for your understanding's sake, number of protons and number of electrons are the same. Okay, because proton is literally like the positive charge of the atom, and electron is the negative charge of the atom. You know, right? In a neutral atom, usually the number of protons will be equal to the number of electrons, unless they are ionized. Do you know what does ionized mean? Ionized means to say it is more positive or it's more negative. It is more positive if there are more protons than electrons. So basically the atom has a charge? Yeah, the atom will have a charge. Okay, or it will be more negative when the amount of electrons is more than the protons. Okay, so that's what we need to know. Okay, so if you look at the definition itself, everything kind of makes sense. All right, atom is a complex arrangement of negatively charged electrons. The keyword is it must be negatively charged electrons are arranged in defined shells about a positively charged nucleus. Okay, this nucleus, which contains the protons and the neutrons, is positively charged. Okay, this nucleus contains most of the atom's mass and is composed of protons and neutrons. So most of the mass is centered here, meaning to say everything else is free empty spaces. Okay, and atoms may form positive ions by losing electrons or form negative ions by gaining electrons. Okay, this one is concept one. Okay, so what we learn now is we learn that atoms is nucleus and electrons orbiting around. Right? Before this model was confirmed, right, or was verified, they had another different model which you guys probably learned in year 9, the plum pudding model. Have you guys learned that before? The plum pudding model basically states that the atoms is like a stupid arrangement like this. I mean, first it sounds stupid now because of the technological advancement, but back then no one could prove it. There was this guy not named Thomson, I think. Thomson's pudding model was that he thought that atoms is like pudding, you know, and then the plum is it's like pudding, and then you have all these charges inside the pudding. Initially he thought this was the model, right? Until this guy known as Rutherford, okay, came up with a gold foil experiment. Okay, so in order to understand this gold foil experiment, I have a very interesting video to show you guys what's going on. Everyone, please pay attention to the screen here.
My curriculum has also used the plum pudding model.
No way lah.
But actually,
no way lah.
no, hold on. It actually does. It's still
To
like,
show you that it's wrong, is it, or what? It's not that dumb, right?
I think it's to show that it's wrong, but it never showed us the rule before.
Yeah.
While performing experiments on radioactivity, Ernest Rutherford bombarded fast-moving alpha particles on a thin gold foil. He observed the reflection of the alpha particles with the help of a screen. Now, according to Thomson's atomic model, an atom consists of a positively charged sphere with electrons embedded in it. So, Rutherford expected that almost all the alpha particles will pass straight and only small deflections will be observed if there would be any. However, Rutherford got totally contrasting results. From his experiment, he made the following observations. First, most of the fast-moving alpha particles passed straight through the gold foil. Second, some alpha particles were deflected through the foil by small angles. And the third point, some alpha particles were deflected by large angles. In rare cases, an alpha particle got deflected by an angle of 180 degrees. Based on his observations, Rutherford derived the following conclusions from his gold foil experiment. First, since most alpha particles passed through the gold foil without any deflection, most of the space inside an atom is empty. Second, very few particles suffered a deflection from their path. Now this means that positive charge occupies very little space inside an atom. Third and final point. As a small fraction of particles got deflected completely by 180 degree, all positive charge and mass of gold atoms are present within a very small volume inside the atom.
Listen up, among everything that this guy said, there are a few things that are extremely important that is always asked in your exam, which is summarized in this diagram here. Okay. First and foremost, in your exam, they will ask you, based on Rutherford's gold foil experiment, how do we know that most of the atom is made of empty space?
Because most are reflected.
Yeah, because this yellow line here, because most alpha particles pass through the gold foil undeflected. When I say most, I mean like maybe 80 to 90% of the alpha particles pass straight through. This yellow line indicates that the atoms are mostly made of empty spaces. Okay, this is the first thing they'll ask. The second thing they'll ask is, how do I prove that the nucleus is positively charged? Which one?
That's one fraction.
Yeah, this small and large deflection proves that this nucleus is made of a positive charge. Because the start of the video said that these alpha particles are positively charged, right? So if you look at the blue and white line here, when the blue color hit close to the nucleus, it will be deflected because positive and positive repel, right? So it deflects a little bit. And if it hits closer to the nucleus, positive and positive will repel, so it got deflected at a larger angle. Okay. And the third thing that they will ask is, how do I prove that most of the mass is in the center nucleus of the atom? It's obviously going to be this rebound one more. Okay, imagine like I have a really fat guy standing here, and then you're a skinny kid who runs into the fat guy, the red color line here, right? So if I run into a really fat kid, then what's going to happen is most likely I'm going to rebound, right? And this guy is going to stay in place, right? So this proves that this red color line proves that most of the mass is located in the center of the nucleus. You understand? This is very important. In this chapter, if they ask about gold-foil, right, you have to know what represents what are yellow line, empty space, large and small deflection proves that the charge is positive in the nucleus, and large rebound is basically because most of the mass is in the nucleus. Understand? This is very important. Always comes out. Always comes out. Okay? So, if you look here, I've already taken the decency to summarize everything you need to know already. Rutherford gold-foil experiment proves that it is positively charged in the nucleus, contains most of the mass in the atom, and has space in between each atom. Most of the mass positively charged, empty space. Okay, surrounded by a cloud of negatively charged electrons, which is here. Okay, and most of the alpha particles pass straight through. Why? Because it is mostly empty space. Some alpha particles are deflected. Why? Because the nucleus is positively charged. Some of them deflect greater than 90 degrees. Why? Because most of the mass is concentrated in the nucleus. In your exam, they'll ask, sometimes I've seen this question be like 3 or 4 marks, and you have to literally explain everything. So, yeah. Make sense? Any questions? No, 100% absorption rate. Good, excellent. That's what I like. Okay, then after that, this part here is basically talking about the element symbol for different atoms already. Okay, like I mentioned, it could this X here represents the element symbol. It could be H, it could be Mg, it could be Cl, it could be like whatever elements that you can see on the periodic table, assuming you take chemistry. Okay, and this number is known as the number on top here is known as pay attention. This number is known as the nucleon number. Nucleon, you see this word, is very weird word, right? Nucleon number is basically the combination of a neutron plus a proton. Right? Basically, this nucleon number says how many things is in the nucleus, okay, which consists of the neutrons and the protons. So let's say, for example, I have 3 neutrons and 3 protons. Then my nucleon number will be, it will be 6, an element, whatever this thing is. Okay. And since I have only 3 protons, right, this number here represents the proton number. Right. So basically what I'm going to write is there's going to be 3 here. Right. So it's going to be like 6, 3x, whatever this thing is. Okay. But don't worry, later you'll get it. Really is the only thing you need to know for the nucleus. Okay, so like I've mentioned, nucleus are made of protons which are positively charged and neutrons which are neutrally charged. The sum of proton and neutron number are known as the nucleon number. Sometimes in your exam, they won't use the word nucleon number or proton number. Sometimes in your exam, when they want to be a real big troublemaker, they'll say mass number and atomic number. Okay, so how do I know which one is which? Like I mentioned, most of the mass is contained in the nucleus, right? So obviously the nucleon number should be the mass number, right? The atomic number is just referring to the proton number only, how much protons are there. Okay, so remember these are very important. Sometimes they'll give you these names instead. Okay, and then after that, we have isotopes. So what are isotopes are? In your exam, they love to ask what an isotope is. An isotope is literally something that is the same element, which contains the same proton number, but different neutron number. For example, same element, same proton number, 111, but different neutron number. Or you could even say different nucleon number is acceptable. Okay, see, 0 neutrons, 1 neutrons, 2 neutrons. All these are all still hydrogen, right? But there are different variations of hydrogen, right? You know, like Cina, Malayu, and Indian, you know, all of them are still human, right? So these are what I call isotopes, okay? Same element, same proton, different neutron. Okay. In your exam, you know what they'll ask you? They'll ask you, this also comes up in your chemistry, they'll ask you, define what an isotope is, which for everyone has already taken chemistry, I'm sure you've seen this question multiple times. You're supposed to say atoms of the same element with the same proton number but different neutron number. If there's more than 2 marks, this answer here will only give you 2 marks. If you see they ask about isotopes and you see 3 marks, right, you need to add one more statement, which is they have the same chemical properties or same chemical behavior or same chemical something, which basically says that we do the same thing. Right? Okay, so this is isotopes. You'll see later in the questions. It's the same thing. Okay, and finally, before I move on, anyone have any questions for this time? Or 100% adoption rate? Anyone online? Okay, and finally, nuclear fission and nuclear fusion. Okay, like I mentioned just now at the start of the introduction to this chapter, we say that fusion is the combination to become one larger atom, right? Fission is the exact opposite. Now, one atom separates into 2 and split and split and split and split and split, and these things will split and 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 split, right? Okay. The only thing they have in common is that they both provide maximum energy. Okay. In your exam, if they ask about this, right, they will usually ask you what is nuclear fusion and what is nuclear fission, which I've already taken the decency of explaining the definition already. Fusion is the opposite of that. It involves taking 2 smaller nuclei and bringing them together to form a bigger nucleus. This is the definition of fusion. Fission is when a large nuclei is split into 2 smaller nuclei, releasing energy in the process. Okay. Now, in your exam, they may also ask you, where does fusion occur and where does fission occur? You see this U here, right? It's literally the same as the U in the sun. So you must remember that fusion only occurs in the sun. Okay. This actually nuclear fusion generates much more energy compared to fission. Right. But because of our limited technology right now, we cannot harness nuclear fusion yet. But the scientists on Earth is already doing something about it again. Maybe right before you die, you can see nuclear fusion taking place, which is much cleaner and much more energy compared to fission. But until then, until you die, most likely, right, you still have to harness energy from nuclear fission, which is where the nuclear power plants generate energy from. Okay, so yeah, you can not much to understand here, You need to know these definitions. Okay, and you need to know, like, you have to have this diagram in your head, and don't confuse. Sometimes some students, they tell me fusion is the separation and fission is the combination, which then awards them with 1 free beating, obviously, right? So make sure you're not that.
What if so when the neutron hits the nucleus,
Yeah,
it splits the nucleus into 2, and then
they release their neutrons to one,
neutrons,
which is used to bombard another nucleus. which then splits into two, releasing their own neutrons, which is used to bombard and blah blah blah. So it's like a chain reaction, if you would say so. Right, it's a chain reaction that keeps on going and going and going. It releases massive amounts of
Okay, at
energy.
the end.
Of course, because this thing here, right, can only like fossil fuel is used to create fire, right? Uranium and plutonium is used for nuclear fission. Eventually, they'll run out. Right, so it's not like an infinite process. If there's something that becomes an infinite process, then it will become free already or valueless. Like for example, the air that we breathe is an infinite process, right? Then it becomes free or valueless, right? Unless you're like some American guy that sells oxygen. Have you seen that stupid story during COVID?
No.
This company in America somehow managed to make something infinite and free sellable. It's so clean air or some shit like that. It's very dumb. Very dumb.
It's COVID.
Yeah. Because the air is dirty, guys. Don't breathe in the COVID air. And here we've got a solution for you. Clean air in the tank. And yeah.
So it's just normal air.
Yeah. It's clean air, filtered air. Okay.
What if the air has COVID in it, but outside of the COVID, you're just gonna get COVID faster.
You'll never know. You'll never know. So a lot of dumb things can work as long as you not get it accident. Alright guys, anyone have any questions? Okay, if you have no questions, please append the questions below. That's the answers in half an hour. If you have any questions, please don't stare at the paper. Please make sure you ask. If not, attend the questions below.
What does this mean?
Which one?
Why are you trying to ask?
State the sign of the charge on this core, bro. What do you think the charge of the core is, positive or negative?
What do you do?
Yeah, that's positive. Like I said, the nucleus is positively charged. Right?
Let's go this question.
You done already?
No, I just asking for which question.
Until you see 5.2, bro.
Oh. Oh, that's it for that. Okay.
Yeah.
Why are you asking? Listen, we are both when you try to get a property that makes as a decision.
Because they have the same, if they're the same element, they must have the same one.
What's it called? Element?
Proton number, bro. They must have the same proton number, that's why they're the same element.
Beta particles are negatively charged, right?
Yeah, but you haven't learned that yet. We can ignore the alpha and beta particles. Question 2C.
The proton and neutron and electron number is the same, right?
Proton and electron number is
That's it.
Yeah. Thanks. Okay, everyone. Are you ready for the discussion? I hope you have attended every question by now. Let's go through the questions together, guys. When we look at this here in Geiger, blah, 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 it's an alpha particle directed at very thin gold foil. As soon as you see this word gold foil, you should remember the video that I've sent you, right? And then from here, you should say that it says that on figure 1.1, complete the path of the 3 alpha particles. You'll notice that this one is very close to the nucleus, so it's only going to suffer a small deflection. This one will go directly straight through, and this one will be rebounding backwards. Right. So you can use this with ruler, right? I'm sure you can get a very decent drawing. And you get 2 to 3 marks for this one. I can't remember, I might have accidentally cut out marks. Now, after that, state the results of the experiment that shows an atom consists of a very tiny charged core containing almost all of its mass in the atom. Right, most of the mass in the core is basically going to be this one, right? When the alpha particles deflect with an angle greater than 90 degrees, alpha particles that deflect with an angle greater than 90 degrees. Bang. There you go. Yeah. Good. Okay. Easy. Now let's take the charge. The charge of this core here obviously is going to be positively charged. And instead, what occupies the space in between these charged cores is basically going to be empty spaces, not electrons. The empty spaces occupy empty spaces. There's basically nothing in between the charged cores, right? And this one here is a very straightforward one. Proton number for sure 2, neutron number is 2. Nucleon number should have been 4. If it's neutron, it's just 2. Okay, everyone? Anyone with any questions for this part here? Good, excellent. Moving on to the next question here. This is a figure 1.11.1 shows the path of 3 alpha particles moving towards a thin gold foil. Once again, it's the video, right? Alpha particles moves directly towards a gold nucleus. If it's towards a gold nucleus, then obviously it's going to deflect at an angle greater than 90 degrees, right? B is moving along a line which passes through close. The keyword here is close to the gold nucleus. So I'm sure it's going to suffer some form of deflection, right? Whereas C does not pass through close to the gold nucleus, then obviously it's going to be one straight line. And from here, once again, they ask you to draw your diagram, which is 3 marks worth. Literally, just remembering the video itself, you can get at least 3 marks from these kind of questions. Right? And state how the results of such an experiment using large number of alpha particles provides evidence for the existence of a nuclei in the gold atom. Nuclei is just a single nucleus, right? So which one is the one that proves the atom? Obviously is these 2 here, right? They're supposed to say something like very few alpha particles scattered at a large angle. Most of them pass through undeviated at empty space, and this is because most of the mass is concentrated in nucleus. So you're going to say something like Small deflection, 90 degrees, and basically everything that we've learned so far. If you written down these 3 keywords, you'll get your marks on. Very easy, very straightforward. Okay. Oh, it should be gold here. Wait. Gold. Okay, moving on. Next. Uranium-238 and uranium-234 are radioisotopes. Isotopes of an element uranium-238 nucleus differs from uranium blah, 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 but both decay by the emission of alpha particles. In terms of particles in each state, how a nucleus of uranium-238 differs from a nucleus of uranium-234. Right. In terms of the nucleus, right, I don't know how much protons will there be, right? But I know that for a fact that this guy will have basically 4 more neutrons compared to this guy, right? So my answer should be they have the same amount of protons, but uranium-238 has 4 neutrons more than uranium-234. Because I only want to care about the composition of the nucleus. Both have the same amount of protons, but uranium-238 has 4 more neutrons. Okay.
That's alright, they're the same element that contain different number of neutrons.
Same element, different number of neutrons. I guess that's acceptable also.
Of such small neutrons.
Yeah, I don't think maybe because I think this one they want you to specify. Because you have to write 4 more neutrons.
Is it because it's too much?
Yeah. Because they ask you to specify, even they will say in terms of particles in each state. Then this is the keyword in terms of particles in each one, right? You state how the blah blah blah. Right. Anyway, moving on. Although the 2 nuclei are different, they are both nuclei of uranium. State a property that makes the isotope the same element. They must have the same proton number, as you can see here. Same proton number. Or even if you wrote same chemical properties or same number of electrons is acceptable. But I would have just written same proton number. Okay,
Sounds good.
this one you skip because you haven't learned anything from this here yet. Then from here, we say most alpha particles pass straight through the gopher undeflected. What does this prove?
So they are contains empty space.
Some alpha particles are deflected the way they came from.
Most of the light particles in there, of course.
Good. Bad. Then you get your 2 marks. Easy. Oh, this is the last question, are you? Okay, guys, then final part here is basically the numbers and everything already, right? Most abundant stable isotope of strontium is strontium-88. The nucleon number is 88, and its proton number is 38, which is X and Y. After that, this one is they already say nucleon number, right? So that one must be X, which is your 88, right? And Y is always your proton number, which is 38. The number of neutrons, you have to minus them. Oh. So it's 40 here, and the number of electrons in a neutral atom, it should be the same as your proton number, right? So it's just 38. Very easy, very straightforward, especially those who take chemistry. Even for those who don't take chemistry, it's not that hard. Then the last part here, strontium-90 is a radioisotope produced by nuclear reaction. State how the structure of this isotope differs from strontium-88. So they already asked you about the structure, how does it differ, right? It's basically defining what an isotope is, which is the same proton number with different neutron numbers, but with the same chemical properties. Same. They don't even care about the same proton number. We just have to mention that they have different number of neutrons, or to be more specific, it has 2 more neutrons, right? So from here, right now, strontium-90 has 2 neutrons more than strontium-88. But yeah, just writing this is good enough, right? And gentlemen, anyone has any questions with regards to everything we've mentioned so far? Okay. Oh, yeah. Anyways, guys, next week we're going to continue on with the syllabus, which is the last part of your radiation already. After that, we'll just have one more chapter to cover, which is space physics, which is a very annoying chapter, in my opinion. But some people really like space, so I guess some of you guys will be able to enjoy that. But I personally hate it. But it's in the syllabus. Anyways, yeah, guys, that's going to be it for today. If you have any questions, you're more than welcome to stay back. If not, enjoy the rest of your night, ladies and gentlemen.